We begin with Chapter 2 of the book of Prigogine, which is titled The Conservation of Energy. Let's start with what are defined as functions of the state. Now, these functions define everything for the thermodynamic system. Of course, the thermodynamic system in equilibrium. The thermodynamic function of state can be completely defined by a certain number of independent variables. For example, the energy, the volume, the number of moles, the different substances. Or, for example, it could be in terms of the temperature, the volume, and the number of moles. Functions expressed in terms of these variables are called functions of state. So, for example, let's consider the case of the ideal gas. The function of state for the ideal gas can be written as an equation of this form for the entropy in terms of the number of moles of a particular particle, N, the mass of those particles which compose the gas, M, the energy, E, and the volume, V, of the system. These functions of state can be determined empirically, and also now some of them can be determined through theoretical considerations. So now please investigate two other examples of functions of state for different systems. For example, the Einstein solid, or a gas and photons, or whatever your preference. So section 2.2, the conservation of energy, let's consider first the case of closed systems. And remember, these are systems in which there is no exchange of matter with the environment. Only energy and work can be done on the system by the external environment. So it is closed to mass, but open to energy and to work. So the first principle of thermodynamics, or the first law of thermodynamics, is that energy is conserved. But that is really for an isolated system, and remember that now we are considering a closed system. So we have to consider the flow of energy from the external environment over the boundary of the system, either into or out of the system. So the total change of energy of the system, dE, is equal to that part of the energy which is coming into the system from the external environment. The change of energy due to processes occurring inside the system, and that is given by the subindice I, dIE is equal to 0. Which means there are no changes of energy within the system due to processes. Now, going back to the first term of equation 1, the energy supplied by the exterior is the sum of a flow of heat, dQ, and the mechanical work which can be done on the system by the environment, which is dW is equal to minus P dV, where P is the pressure and V is the volume. This is the pressure normal to the surface. So therefore we can write equation 2, which is just the total change of energy of the system is equal to dQ minus P dV. Now the minus is there because if you reduce the volume, V, that means dV is negative. That gives us a positive term, so that increases the energy in the system. Of course, if you squish the system or reduce the volume, you are going to be increasing the energy within the system. Consider a system undergoing an internal change characterized by chi. Let E, the energy, be a function of state, and we assume that it can be expressed in terms of the variables V, the volume, T, the temperature, N, the number of moles, N1, so on, until Nc for the different components 1 to C in the system. Now, As we have seen in the previous class, in the previous chapter, the mole numbers can be expressed in terms of Chi. Therefore, the energy becomes a function of the volume, the temperature, and Chi. Therefore, the total differential of the energy E can be written in the form of equation 3. dE is equal to the partial of E with respect to volume at constant temperature and Chi. Chi is the advancement of the reaction, times dV, plus the partial of E with respect to the temperature, constant volume, and Chi, times dt, plus the partial of E with respect to Chi at constant temperature and volume, times dG. Now, using equation 2 for dQ in terms of dE and pdV, we can write equation 3 in this form of equation 4, where these new variables we have introduced are represented in equation 5. The first term is the heat capacity at constant volume and advancement of the reaction. The second term is the heat effect of compression at constant temperature and constant advancement of reaction. And the third final term of equation 5 is the heat of reaction at constant temperature and volume. And this will be positive for exothermic reactions and negative for endothermic reactions. Now, for convenience, let's define a new variable which we will call enthalpy. Enthalpy H will be defined as the internal energy E plus the pressure times the volume of the system. So therefore, dH would be equal to dE plus pdV plus vdP. Now we can write the previous equation as dH is equal to dQ plus vdP, using the fact that we have seen in earlier slide that dE is just equal to dQ minus pdV, where dQ is the infinitesimal movement of heat. Now, just as we did in the previous slide for dE, we can write for dQ, we can write dQ in the form of equation 8, where these new variables now, the specific heat and the specific enthalpy and the heat of reaction, are given by equations 9. And you can do that for yourself. Just check that we get equation 8 by using equation 9 and equation 7. Now remember, we can write the number of moles for substances 1 to C, that is N1 and so on to NC, instead of Chi, which is the advancement of the reaction. We saw that in chapter 1. So therefore, we can write equation 8 in the form of equation 10 by defining a new term, which is the specific enthalpy, which is the small h as indice with an indice component gamma of the form of equation 11. So what we have done is substituted Chi for N1 to NC, and then just use that in equation 8 to give equation 10 with this new variable, the specific enthalpy, H sub indice gamma, where gamma represents the different components in the system. So you can check that for yourself, plugging in equation 11 in equation 10 and then deriving equation 8. Here in equation 11, the variables which are held constant are the pressure, the temperature, and all other mole numbers except the mole number that we are doing the differential with respect to. So that this n prime gamma denotes all mole numbers n1 to c, with the exception of n gamma, the one that we are doing the differential with respect to. Now we can define yet another form of enthalpy, which we denote as the specific enthalpy of component gamma per unit mass, which we denote by this plus sign in the superindice. So we have little h plus and under indice gamma. And that's just equal to partial h by partial m gamma, where m gamma is the mass of substance gamma, holding the pressure, the temperature, and all the other masses of the other substances constant. And you can see that that is just 1 over the molar mass of substance gamma times h gamma, the specific enthalpy per mole of substance gamma. This is equation 12. Now let's consider the case of open systems. Previously we were discussing closed systems in which we only allow a flow of energy over the boundary or work to be done on the system, which can also change its internal energy by doing work on the system. Now we are going to consider open systems, and this is a system in which we allow both energy and mass to flow over the boundary of the system, and we can also do work on the system. Now, for this case, the case of an open system in which there can be mass flow over the boundary, in the conservation of energy, we must take into account the exchange of matter with the exterior, because this matter can also carry with it internal energy. For example, the material may be hot, so it would add energy to the system. So in this case, instead of equation 2 for the differential of the energy, the internal energy, we have instead dE is equal to d phi minus p dV, where this phi, instead of, remember for the case in the closed system we had dQ, dE is equal to dQ minus p dV. Here we are using d phi, where phi now is the resultant flow of energy due to the heat transfer, that means the heat Q, and due to the exchange of matter, because that matter can also take energy into the system with it. So we can write d phi is equal to dQ, the flow of heat, plus dEm, which is the energy coming in on the matter which is coming into the system, because it is now an open system. Now the equation for the enthalpy then becomes dH is equal to d phi plus v dP. So instead of dQ, which we had before, we now have d phi. Now, we know that when we are resolving problems in physics, that the energy is only defined up to an arbitrary additive constant. That means it doesn't matter where we put the coordinate energy equal to 0. What is important in physics is the differences, the changes in energy, and not the absolute value of the energy. And so that is also the case for the enthalpy. The enthalpy, just like energy or entropy, is defined apart from an arbitrary additive constant. So we can signify that by writing h prime is equal to h plus alpha, where alpha is this arbitrary additive constant. Now consider the case for an open system in which we assume that the mass being brought into the system or being exposed to the environment is the same mass within the system or in the environment, so that we have a homogeneous system. Therefore, alpha is not really a constant, but will be proportional to the mass of the system M. And it is therefore no longer a constant for open systems. Therefore, for the case of open systems, it follows that the change of enthalpy, or the energy in an open system, is defined apart from the term beta, some constant, in this case a real constant, times dm, the change in mass of the system. And this also applies for d phi, which is the infinitesimal change in the energy of the system. That is, the energy being brought into the system through the flow of heat, or because it's attached to the material which is being brought into or given out by the system. Now let's look at a particular example. Assume that we have two subsystems, 1 and 2, and that each subsystem is open to itself, but the whole system is closed. So therefore, for each subsystem, we will have the infinitesimal change in the enthalpy is equal to d phi plus v dp. The same for the two subsystems. Furthermore, we also assume that P1 is equal to P2 is equal to P. That is, the pressure in both of the subsystems is identical. Therefore, summing up the two equations 17, we get equation 18, where V is equal to V1 plus V2. That is the sum of the two volumes of subsystem 1 and subsystem 2. Now, since the system, the sum of the two systems as a whole, is closed, it must obey the usual formulation of the first law, which is the conservation of energy for that system. And in terms of the enthalpy, that is just dH for the system, is equal to dQ plus V dP. dQ, remember, is the heat which is exchanged with the external environment, V the volume of the system, and P the pressure. So this dP is the change in the pressure over the system, which is the work done on the system. V dP is the work done on the system by the environment. Therefore, comparing equation 19 with equation 18, we can derive that dQ is equal to d1 phi plus d2 phi. So remember, d1 phi is the heat flowing into system 1 from the environment and from system 2, plus the energy in the matter which is coming in from system 2 into system 1, or leaving system 1 and going to system 2. And the same for d phi 2, d2 phi. So as I just said, d1 phi then is equal to d1 q external E, that's why the sub-indice E, plus d1 phi I. So the first term is the heat coming in from the environment, the external environment, into subsystem 1, and the second term is the heat coming from subsystems 2 into subsystem 1, plus the energy coming from subsystem 2 into subsystem 1, which comes in with the matter because the system is open between 1 and 2. There is no boundary, so it's an open system between 1 and 2. And the same for d2 phi. Now, the total change of heat, or dQ, for the whole system, subsystem 1 plus subsystem 2, has to be equal to d1Q external, coming in from the external environment, plus d2Q Q coming in from the external environment is equation 22. Therefore, putting equation 22 into equation 20 and using equation 21, we can derive that d1 phi internal plus d2 phi internal is equal to 0. You can do that, it's just algebra. Check it for yourself, please. So that just says that the energy flow received by subsystem 1 from subsystem 2 is equal and opposite in sign to that received from subsystem 2 from subsystem 1. Now, if the subsystems were close to each other, so we only allow the flow of heat, then equation 23 can be written as equation 24 because there is no flow of matter, so we don't have to include the energy on the matter which is being exchanged between the two subsystems. So then we have just d1q plus d2q is equal to 0. And that's just the expression for the conservation of energy for the system.